Our sun could be encased by a colossal machine within a few centuries. This Dyson Swarm represents the ultimate energy source, a concept moving from science fiction into serious engineering plans. I will give you the complete blueprint for building this star-scale machine, from the fundamental physics to the final ethical questions. What does it truly take for a civilization to harness the power of its star, and what unforeseen dangers might lie in such an immense project? How far are you willing to see human ambition reach? A star flickering not from natural cycles but from the deliberate motion of trillions of orbiting structures is our destination. This is the Dyson Swarm, a vision physicist Freeman Dyson proposed not as a solid shell, but as a vast, decentralized cloud. Each element in this celestial fleet is an independent power station, and together they form a single, star-encompassing machine, the ultimate expression of a civilization's reach. This concept elevates us from planetary inhabitants to stellar engineers, a defining trait of what scientists call a Kardashev Type II civilization. The beauty of the swarm lies in its elegant simplicity and its inherent scalability. You do not build it all at once. You start with a single collector, then 10, then 1,000,000, growing the constellation over generations. This modular approach means the project can begin with technology we can almost envision today, expanding steadily to capture more of the sun's colossal energy output. That energy, once lost to the void, becomes the lifeblood for an unimaginable future. But to even begin this project, we must first master the fundamental forces that hold our solar system together. That raw power, a continuous nuclear furnace, defines the very challenge we face. Every second, our sun releases energy equivalent to billions of nuclear bombs. To capture even a tiny fraction of this output is to transform a civilization, but you cannot simply build a power cord to a star. The principles of stellar energy capture begin with understanding the light itself. The sun behaves like a near-perfect blackbody, a theoretical object that emits radiation across a spectrum based solely on its immense temperature. This gives us not just visible light, but a broad river of energy, from infrared heat to ultraviolet rays. The amount of this energy reaching a specific point in space is governed by the solar constant, a measure of the sun's power flooding past Earth. But this energy does not stay concentrated. It obeys the inverse square law, a simple but profound rule of physics. As you travel outward from the sun, the energy spreads out, becoming dramatically less dense. At the distance of Mercury, the light is intensely concentrated and ferociously hot. By the time you reach the orbit of Earth, that same bundle of energy has thinned considerably. This law dictates the entire architecture of the swarm. Do you build closer to the sun for greater energy density, forcing your technology to withstand hellish conditions? Or do you build farther out in a gentler environment, but then need vastly more collectors to gather the same amount of power? The choice is a fundamental trade-off between material science and sheer scale. Efficiency becomes the holy grail. Even the most advanced solar panels we can conceive of today operate far below the theoretical maximum for converting light to electricity. Pushing towards 100% efficiency, a concept physicists call quantum efficiency, requires materials that can catch nearly every photon and convert it into usable energy. This is not just about better semiconductors. It is about managing the intense heat that comes with such concentrated power. A collector close to the sun must radiate away immense waste heat to avoid melting into a pool of liquid metal. This demands materials that can reflect what they do not absorb and withstand relentless particle radiation. all while maintaining their structural integrity for centuries. Without mastering these foundational principles of physics and energy conversion, the grandest designs for a Dyson Swarm would remain just a beautiful dream. The collector itself, the fundamental unit of this celestial fleet, is where these brutal physical realities meet engineering ambition. Each collector unit is essentially a city-sized power plant floating in the void, a delicate balance of extreme forces. Its primary surface is a vast solar sail, thinner than a sheet of paper yet spanning kilometers. This sail is studded with ultra-efficient photovoltaic cells, but the real magic lies in the materials holding it all together. We are talking about nanomaterials like graphene, a substance just one atom thick yet stronger than steel. This incredible strength-to-weight ratio is not a luxury, it is an absolute necessity. The lighter the collector, the less energy is needed to maneuver it, and the cheaper it is to launch from its manufacturing point. But strength alone is not enough. The side of this collector facing the sun will be baked at temperatures high enough to melt most metals. This is where thermal management becomes a matter of survival. The collector cannot simply absorb all that heat. It must radiate it away into the cold of space. Sophisticated cooling systems, perhaps using fluids that boil and condense in closed loops, would work like a car radiator on a cosmic scale, pumping heat to radiator fins on the structure's shaded side. Without this constant heat rejection, the entire unit would quickly become a molten blob. Then comes the question of what to do with all the power you have generated. You cannot run a wire through space, so each collector needs an integrated power transmission system, likely a focused microwave or laser beam. This energy would be precisely targeted at a central receiver, perhaps located in a stable orbit for collection and redistribution. But space is not empty. It is a dynamic environment filled with micrometeoroids and the constant threat of collision with other collectors. This demands a level of autonomy we are only beginning to develop. An onboard artificial intelligence would constantly make minute adjustments, firing tiny thrusters to maintain its precise orbital slot and to avoid debris. It might even manage self-repairing mechanisms, using robotic arms or stored patches to fix minor damage from particle impacts. These are not just simple satellites, they are intelligent, resilient nodes in a vast network. The design of this single unit, this building block, dictates the entire project's cost and timeline. Perfecting one is the first step, but what happens when you need to build not one, but trillions of them? Building trillions of these collectors demands a manufacturing revolution that makes every factory on Earth look like a single workshop. The numbers are so vast they defy human comprehension. To even approach this scale, we cannot rely on shipments from Earth. The fuel and cost would be astronomical. Instead, the industry must move to the source of the raw materials, leading us to the asteroid belt. This region is not the crowded field of tumbling rocks you see in movies, but a vast frontier rich with the very metals, minerals, and water we need. Here, in the deep quiet of space, we would establish the first self-replicating factories. This idea, often called a von Neumann machine after the mathematician who explored its logic, is the only way to achieve the necessary exponential growth. Imagine a single factory, a complex of autonomous robots and 3D printers the size of city blocks. Its first and only mission is to create a perfect copy of itself. It uses robotic miners to extract nickel and iron from a captured asteroid. It refines these metals, fabricates new structural beams, circuit boards, and thruster components. Slowly, over months or years, a second factory takes shape right beside the first. Now there are 2, then 4, then 8. This geometric proliferation turns a single seed into an industrial ecosystem capable of churning out collector units not by the thousand, but by the billion. The technological hurdles are immense. The artificial intelligence running these facilities must be incredibly robust, capable of diagnosing its own malfunctions and performing complex repairs without any human guidance for years at a time. Every system, from the smelters to the assembly arms, must be designed for near-perfect reliability. There can be no supply chain for spare parts. The factory must be its own supply chain, recycling every scrap of waste and repurposing broken components in a perfectly closed loop. This is a complete rethinking of industry where the concept of waste ceases to exist. But what is the point of building countless units if they remain stacked in an orbital warehouse? This colossal production effort is only the first half of the equation. The true test begins when we must deploy this endless stream of hardware into a precise and harmonious dance around the sun. Launching a single satellite into orbit is a complex ballet of physics, but launching trillions into a coordinated dance around the sun is a challenge of almost unimaginable scale. The goal is to create a stable, continuous cloud of collectors, each one tracing its own perfect path without ever interfering with its neighbors. This is not a random scattering, it is a meticulously planned celestial architecture. The fundamental tool for placing these collectors is the Neumann transfer orbit, an energy-efficient path that uses the sun's gravity itself as a slingshot. Imagine a spacecraft firing its engines just twice, once to leave a stable orbit and again to settle into a new one farther out. This elegant maneuver is the interstate highway of the solar system, the route that most of our collectors would follow from their asteroid belt factories to their final working positions. But the solar system is not a blank slate. It is filled with gravitational hills and valleys. These are the Lagrange points, special positions where the gravitational pull of the Sun and a planet like Jupiter perfectly balance the orbital motion of a smaller object. Placing relay stations or command centers at these points creates stable anchors in the cosmic ocean, perfect hubs for managing the flow of energy and traffic. Yet even a perfectly placed orbit is not permanently fixed. Over time, the subtle gravitational tugs from planets cause an orbit to slowly rotate, a phenomenon called precession. For a Dyson Swarm, this is not a flaw but a feature. By carefully calculating these shifts, engineers could design the entire swarm to slowly precess as a single unit, ensuring that every collector maintains its relative position for centuries, a self-correcting clockwork on a stellar scale. But how do we get these massive structures moving in the first place, overcoming the immense gravity wells of planets and moons? The answer lies not in chemical rockets, but in fundamental forces. Electromagnetic launchers, or mass drivers, could use powerful magnetic fields to hurl raw materials or even finished collectors off the surface of an airless moon like Luna. Think of it as a cosmic catapult, accelerating payloads to escape velocity without a single drop of fuel. For Earth itself, the ultimate solution might be a space elevator, a ribbon of carbon nanotubes stretching 36,000 kilometers into the sky. An elevator car climbing this tether could deliver payloads to orbit with the efficiency of a train ride, finally breaking our dependence on expensive and polluting rockets. Once this river of hardware is flowing into space, a new and terrifying problem emerges: traffic management. The sheer number of moving objects creates a logistical nightmare where a single collision could trigger a chain reaction of destruction, a cascade of shrapnel known as the Kessler syndrome, but on a solar scale. Preventing this requires a planetary nervous system, a distributed artificial intelligence of staggering complexity. Each collector would constantly communicate with its thousands of nearest neighbors, reporting its position, velocity, and intention. The central AI would act as a cosmic air traffic controller, not micromanaging every unit, but setting broad traffic laws and allowing the swarm to self-organize, making trillions of tiny course corrections every second to maintain safe distances. This system would need to be resilient, able to absorb the loss of thousands of nodes without the whole network collapsing into chaos. It is a digital ecosystem that must be as stable and enduring as the orbital mechanics it manages. Yet, even with this celestial ballet perfectly choreographed, a final question remains. The energy has been harvested, the swarm is stable, but how do we get that unimaginable power back to a waiting Earth or to the fledgling colonies on Mars? That immense power, harvested by countless collectors, must now travel across the void to where it is needed. The solution cannot be a physical cable stretching millions of kilometers. Instead, the swarm relies on an invisible grid of light and microwaves, a celestial power network where energy is beamed across the solar system. This technology, wireless power transmission, turns electricity into a tightly focused beam that can be aimed at a distant target. The principle begins with conversion. Inside each collector, the generated electrical current is transformed into either microwaves or coherent laser light. Think of a microwave oven, but instead of heating food in a box, its energy is focused into a narrow, directional beam that can travel for millions of kilometers without significant spreading. For laser transmission, it is like a laser pointer, but one with the power of 1,000 nuclear reactors, its light perfectly aligned and coherent. The challenge is not just creating the beam, but keeping it perfectly on target. Over the vast distance from the swarm's orbit to Earth, even a microscopic error in aim could mean the beam missing its mark entirely. Each transmitter would need a sophisticated guidance system, constantly tracking its intended receiver and making minute adjustments to account for the orbital motions of both the sender and the receiver. This requires atomic-level precision, a targeting system that never falters, and there are losses. No process is 100% efficient. Energy is lost when converting electricity to the beam. More is lost as the beam travels through space, and still more is lost when converting it back to electricity on the ground. Even with advanced technology, these cumulative losses could mean that only half of the power sent actually arrives. This staggering inefficiency is simply the price of doing business across interplanetary distances. It forces the system to be built on a gargantuan scale, sending twice as much power to get the desired amount. This leads to the most critical concern: safety. A misaligned power beam, especially one carrying terawatts of energy, would be a weapon of unimaginable scale. A microwave beam straying over a populated area could act like a global microwave oven, causing catastrophic heating. A laser could slice through cities. Therefore, the system must be designed with unbreakable fail-safes. Multiple independent targeting systems would constantly cross-check each other. The beam itself might be encrypted with a complex signal, and if the receiver ever loses that signal for even a millisecond, the transmitter would instantly shut down. The entire network would be designed to fail safely, turning itself off at the slightest hint of an error. On the receiving end, you would find the rectina, a vast field of simple metal mesh that acts as the target. This rectifying antenna converts the incoming microwave energy back into direct current electricity. These structures would need to be enormous, spanning hundreds of square kilometers to capture the diffuse energy of the beam after its long journey. They would be located in remote, secure areas far from population centers as a final layer of safety. But once this grid is established, a new kind of power emerges, one that flows not just through wires but through the fabric of controlled space itself. The civilization that masters this has access to nearly limitless energy, raising profound questions that transcend engineering. Who decides where the power goes? Who controls the spigot for the sun? This immense capability forces us to confront the ultimate purpose of such a project and the responsibilities that come with wielding the power of a star. The very fabric of our celestial machines depends on a revolution in what we can build with. A material that is lighter than air yet stronger than steel is not a fantasy, it is a prerequisite. The collector units we described earlier would be vaporized in moments by solar radiation and micrometeoroid impacts without a skin made of something truly extraordinary. This is the core challenge of material science for the Dyson Swarm, a quest for substances that defy our everyday experience. The most promising candidates emerge from the atomic scale, from the world of nanomaterials. Carbon nanotubes are a perfect example. Imagine rolling a sheet of graphite, the same material in a pencil, into a perfect cylinder just one atom thick. This creates a structure with a tensile strength hundreds of times greater than steel, yet with a density that is almost negligible. These nanotubes could form the backbone of the collector's frame, providing a skeleton of incredible resilience. Then there is graphene, a single layer of carbon atoms arranged in a hexagonal lattice. It is not just strong, it is an excellent conductor of both electricity and heat, making it ideal for the collector's skin, where it could help distribute and radiate away the intense thermal load. But even these wonder materials have limitations. They can be brittle, and a single atomic flaw can become a point of catastrophic failure. The solution may lie in combining them, creating graphene composites where nanotubes are woven into a larger matrix, creating a material that is tough, not just strong, able to deform slightly without shattering. Beyond known substances, laboratories are experimenting with metamaterials, engineered structures with properties not found in nature. Imagine a substance programmed to self-heal. A micrometeoroid, smaller than a grain of sand but traveling at hypersonic speed, punches a tiny hole in a solar sail. Instantly, a network of capillaries within the material releases a two-part resin that fills the void and solidifies in the vacuum of space, restoring integrity without any human intervention. Or consider aerographite, a foam of carbon tubes that is so light it can be balanced on a dandelion puff, yet it can compress and spring back to its original shape. This could be used for shielding, absorbing the kinetic energy of impacts. The research from institutions like MIT points toward programmable matter, materials that can change their properties on demand. A collector might stiffen its structure when maneuvering, then become more flexible to dampen vibrations. The ultimate goal is a material that is not just a passive component, but an active participant in its own survival. Yet, creating a gram of this material in a lab is one thing. Producing it by the megaton in an automated space factory is another. The manufacturing process must be as elegant as the material itself, likely involving molecular assembly or advanced chemical vapor deposition, where materials are built one atom at a time with perfect precision. This is not a separate challenge from the industrial replication we discussed. It is the very heart of it. The factory must be designed around the material, and the material must be designed for the factory. Without these tangible breakthroughs in what we can build with, the grandest blueprints for a Dyson Swarm are just intricate drawings on a page. But turning these atomic-scale discoveries into a star-encompassing reality requires a resource far more elusive than carbon, the astronomical capital to fund it all. The price tag for a Dyson Swarm is not measured in trillions, but in the complete restructuring of our global economy. Every war, every infrastructure project, every space program in human history would amount to a rounding error in this budget. Financing such an endeavor demands a new economic paradigm, one that operates on a solar system scale. The capital would likely flow from 3 interconnected sources. A unified Earth government representing all of humanity would provide the foundational public funding, a long-term investment in our species' future. Alongside this, private mega-corporations would invest staggering sums, anticipating returns not just in monetary profit, but in the ultimate commodity, energy itself. Their investment would be banked on the promise of generating power so cheap and abundant it would pay for the entire project millions of times over. The third pillar involves entirely novel models like claiming and monetizing celestial resources. An asteroid mining corporation might not just sell platinum, but earn perpetual royalties from every watt of energy generated by the collectors built from its metals. This shifts the concept of return on investment from quarterly reports to a timescale of centuries. The real profit is not in currency, but in capability. The energy surplus unlocks everything. It powers the mass drivers that make interplanetary travel routine. It fuels the atmospheric processes that could one day terraform Mars. It runs the supercomputers that solve diseases and model climate systems with ease. This is an economy built on joules, not dollars, but money and machines are nothing without coordination. The logistics of mobilizing this effort dwarf the financing. It requires a workforce of millions both in space and on Earth, supported by billions more in automated systems. This is not a project for a single nation or a single generation. It demands an unbreakable framework of international cooperation, a shared vision that can survive the rise and fall of governments, economic booms and busts, and the natural short-sightedness of human politics. The blueprint must be resilient, designed to continue autonomously even if political will on Earth temporarily falters. The economic and social foundations must be as durable as the carbon nanotube threads holding the swarm together. With a financial and logistical framework in place, a more profound question emerges, one that goes beyond engineering and economics. Who gets to control this star-encompassing machine, and what rights does a species have to reshape its entire solar system? This vast celestial machine cannot be managed by human hands. Its trillion moving parts, each a city-sized power station, demand a mind capable of thinking on a solar system scale. The true nervous system of the Dyson Swarm would be a super-intelligent artificial intelligence, a silent guardian overseeing every facet of construction, deployment, and maintenance in real time. This is not a simple control program. It is an autonomous entity of staggering complexity, making trillions of decisions every second. Its primary task is navigation, solving an endless stream of orbital mechanics problems to ensure no two collectors ever collide. But its duties extend far beyond traffic control. This AI would be a master diagnostician, constantly monitoring the health of every single unit. Using advanced machine learning, it would predict failures before they happen. A slight dip in power output from a collector millions of kilometers away, a tiny pressure loss in a cooling loop, a minuscule drift in its alignment, these subtle anomalies would be detected instantly. The AI would then dispatch a tiny repair drone from a nearby depot, or in some cases, instruct the collector to use its own robotic limbs to apply a self-healing patch, all without a single human being ever knowing there was a problem. This predictive maintenance is the only way to prevent a cascade of failures in a system too large for direct oversight. But how does such an intelligence make decisions? It would likely use a hybrid approach. A central superintelligence would handle the grand strategy, the long-term orbital patterns and energy distribution goals. Yet it would grant a degree of autonomy to the swarm itself, employing principles of swarm intelligence. Each collector would communicate with its neighbors, forming local consensus on minute course corrections. This decentralized decision-making makes the system resilient. If a solar flare wipes out 1,000 collectors and damages the communication network, the local groups can continue to maintain safe distances and stable orbits, preventing a catastrophic chain reaction. This leads to the most critical function, defense. The swarm is fragile, a cloud of thin foil and delicate machinery. A large interstellar object, perhaps a rogue comet nucleus from deep space, could tear a devastating path through the constellation. The AI Overseer would be our first and only line of defense. It would track such threats years or even decades in advance, calculating their trajectories with atomic precision. It might then commandeer thousands of collectors, using their focused power beams not to transmit energy, but to gently nudge the incoming threat, a tiny push applied over millions of kilometers, just enough to alter its course and save the swarm. Yet, entrusting the power of a star to a non-human intelligence forces us to confront a profound ethical dilemma. How do we ensure this godlike machine remains our faithful steward? Its programming must be imbued with unbreakable ethical constraints, a core directive that its sole purpose is to serve and preserve humanity. It must be immune to misinterpretation, to any temptation to optimize for energy production at the expense of human life. We would be creating a partner in our cosmic ambition, a silent, watchful mind ensuring our greatest project does not become our final mistake. A solar flare is not just a burst of light, it is a storm of high-energy particles racing outward at near light speed. For a Dyson Swarm, such an event is the equivalent of a hurricane made of radiation, capable of overloading and frying the delicate electronics of millions of collectors in a single wave. The engineering response to this invisible threat is a layered defense. Each collector would be sheathed in advanced radiation shielding, perhaps layers of hydrogen-rich polymers or even water ice stored within its structural cavities, acting as a barrier to stop those penetrating particles. But shielding alone adds immense mass, so the system's true resilience lies in its intelligence and agility. Upon detecting the first signs of a solar eruption, the swarm's overseeing artificial intelligence would command a synchronized maneuver. Like a field of sunflowers turning away from a harsh wind, the entire constellation could temporarily reorient, turning their fragile edges toward the onslaught to present the smallest possible cross-section to the storm. Critical systems would be powered down into a safe mode, and redundant circuits, isolated deep within the structure, would stand ready to take over if primary systems are damaged. This is not a one-time fix, but a constant dance with the sun's violent moods. Then there is the threat you can see, or at least track, the relentless rain of micrometeoroids and human-made space debris. A particle smaller than a grain of sand, traveling at 20 kilometers per second, carries the kinetic energy of a bowling ball thrown at 100 miles per hour. Against the thin foil of a solar collector, it acts like a cannonball. Passive defense begins with a concept called the Whipple shield, a simple yet brilliant design of spaced layers. An impacting particle hits the outer bumper's shield and vaporizes, spreading its energy into a cloud of gas and smaller fragments that then harmlessly pepper the main backing wall. Scaling this up for a Dyson Swarm means designing collector surfaces as multi-layered skins, with outer sacrificial sheets absorbing the initial brunt of these tiny impacts. But for larger debris, passive shielding is not enough. This demands active defense, a point defense network integrated throughout the swarm. Imagine a system of small, powerful lasers mounted on specialized Guardian platforms. Their sole job is to constantly scan their local volume of space. When their sensors identify an incoming object, from a pebble to a lost bolt, the laser fires a brief, precise pulse. This does not blast the debris to pieces, but rather vaporizes a tiny portion of its surface. The resulting jet of superheated gas acts like a microscopic rocket thruster, gently nudging the object onto a new trajectory that misses all the collectors. This constant, silent ballet of vaporization and deflection would be happening thousands of times per second across the entire swarm, a digital immune system neutralizing threats before they can cause harm. The long-term survival of this star-scale machine depends on this proactive and dynamic resilience. It must be more than a collection of parts. It must be a living system, able to absorb shocks, heal its wounds, and adapt to an environment that is constantly trying to tear it apart. Overcoming these cosmic hazards transforms the swarm from a fragile concept into a permanent feature of our solar system, a resilient infrastructure that allows us to finally turn our attention from mere survival to the profound purpose of all that gathered power. This immense undertaking unfolds not in a single lifetime, but across a 1,000-year calendar. Its construction is a symphony in multiple movements, each phase building the foundation for the next, transforming an impossible dream into an inevitable reality. The very first step is deceptively simple, a prototype swarm nestled safely in Earth's orbit. Here, we would test the core technologies on a manageable scale. A few dozen collector units would be launched, their delicate sails unfurling to practice the intricate dance of energy capture and wireless transmission back to a ground station. This orbital laboratory would prove the resilience of our nanomaterials against real solar radiation and perfect the autonomous navigation algorithms that will one day govern trillions. Success in this initial phase gives us more than just data. It builds the political and economic confidence needed for the next, far more ambitious leap. Phase 2 shifts the entire industrial base off-world. Using the mass drivers and initial space elevators we perfected, we established the first self-sufficient factories on the Moon. Their goal is not to build collectors, but to build the factories that will build the collectors. These lunar outposts, powered by the sun and fed by local resources, become the training ground for our von Neumann machines. They learn to replicate using the regolith under their feet, creating an industrial ecosystem that is no longer tethered to Earth's gravity well. From here, the project's center of mass moves to the asteroid belt. These celestial mines provide the bulk metals and water, and it is here that the first major orbital foundries come online, beginning the exponential production of collector units. This is the point of no return, where humanity becomes a truly multi-planetary species, its economy rooted in the solar system itself. With a river of hardware now flowing from the belt, Phase 3 begins the swarm's true expansion. We do not attempt to encase the sun all at once. Instead, we construct a single, dense ring around the sun's equator, a glittering bracelet of power stations. This initial ring is strategically chosen for its orbital stability, a proving ground for the solar-scale traffic management system. Achieving the first major milestone, capturing just 1% of the sun's total output, would already provide thousands of times more energy than all of human civilization uses today. This power is not sent back to Earth, but is used right there in space to fuel the exponential growth of the construction effort itself. The swarm begins to power its own expansion. Subsequent centuries see this ring slowly thicken and spread, reaching toward the sun's poles in a gradual, controlled fill. Each new collector placed into orbit adds its voice to the chorus, and with every passing decade, the constellation grows denser. Milestones are marked by the establishment of the first permanent power beam to a Martian colony, or by the swarm's artificial intelligence successfully navigating a major coronal mass ejection without significant losses. The project becomes the enduring backdrop of human civilization, a multi-generational endeavor that defines our purpose. This phased approach is our greatest tool against the sheer scale of the task. It allows for course correction, for new technologies to be integrated, and for each generation to contribute a tangible, achievable piece to an epic that will outlast empires. What kind of society would we need to become to maintain such a vision across 50 generations? Every single kilogram we lift from Earth's surface fights an invisible, crushing weight. This is the tyranny of the rocket equation, a brutal law of physics that dictates most of a rocket's mass must be fuel just to carry the fuel needed to reach orbit. For a project requiring trillions of tons of material, conventional rockets are a financial and physical impossibility. We must find a way to leave our planet not with a controlled explosion, but with the efficiency of a train ride. The most elegant solution is the space elevator, a concept that sounds like science fiction but is grounded in known physics. Imagine a ribbon, a tether made of carbon nanotubes, stretching 36,000 kilometers from the Earth's surface to a counterweight in geostationary orbit. Electric elevator cars would climb this ribbon, carrying payloads at a fraction of the cost of any rocket. The challenge is monumental, manufacturing a single, flawless cable of that length and strength and protecting it from space debris and atmospheric storms. But if we could build it, the economics of space would transform overnight. For locations with weaker gravity, the equation simplifies dramatically. The Moon, with just 1/6 of Earth's gravity, is the perfect platform for a mass driver. This is essentially an electromagnetic railgun, a long track that uses powerful magnetic pulses to accelerate a payload to lunar escape velocity. Without an atmosphere to create drag, a cargo pod containing raw metals or a pre-assembled collector could be launched silently into space, its trajectory perfectly calculated for an intercept with a waiting orbital factory. The energy cost is trivial compared to a rocket launch, paid for by the abundant solar power available on the lunar surface. An even more advanced concept is the orbital ring, a structure that encircles the entire Earth, spinning just above the atmosphere. This ring would be held in place not by rockets, but by the centrifugal force of a superconductor cable moving at incredible speeds inside it. Elevators from the surface would not have to climb 36,000 kilometers. They would only need to reach this low-flying ring, a few hundred kilometers up. Once you dock with the ring, you are already in space, and magnetic sleds could then accelerate you to any desired orbital velocity. The initial construction of an orbital ring would be a project rivaling the Dyson Swarm itself, but its payoff is a permanent, two-way highway to space. Each of these launch systems represents a different path to the same goal, breaking the chains of our planetary gravity well. The choice is not which one to build, but in what sequence. We might start with lunar mass drivers to bootstrap the off-world industry, use that capacity to assist in constructing a space elevator, and eventually, centuries from now, encircle our world with an orbital ring. The common thread is a massive upfront investment in infrastructure, a bet on a future where the resources of the solar system are ours to use. Without solving this fundamental launch dilemma, the Dyson Swarm remains a beautiful dream trapped by gravity on the very world that conceived it. But what happens when we finally break free and the river of material begins to flow? How do we transform this raw matter into the intelligent, self-replicating factories that will build our star machine? A metallic asteroid drifting silently for billions of years suddenly shudders as a robotic claw bites deep into its surface. This is not a scene of destruction, but of creation. The practice, known as in situ resource utilization, or as RU, is the absolute bedrock of the entire Dyson Swarm project. Its philosophy is simple yet revolutionary. Do not bring your materials from Earth, find them and use them where you are. The cost of launching even a single kilogram of water or metal from our planet's deep gravity well is astronomically high. To build trillions of collectors, we must become citizens of the solar system, feeding our factories with the raw abundance already floating around us. The first step is the Cosmic Prospector, an autonomous spacecraft equipped with advanced spectrometers. It does not just look at an asteroid, it reads its elemental signature from a distance, identifying the perfect candidate, a metallic M-type asteroid rich in iron, nickel, and cobalt, or a carbonaceous C-type loaded with water and organic compounds. Once a target is selected, the real challenge begins: capturing it. You cannot simply lasso a mountain. One method involves a solar sail tug, using the gentle but constant pressure of sunlight to slowly, over years, nudge the asteroid into a stable orbit around a Lagrange point, a gravitational parking spot where our factories await. Another, more direct approach might use a swarm of smaller bots that land on the surface and fire their thrusters in unison, collectively steering the colossal rock. With the asteroid secured, the robotic miners go to work. These are not the giant machines of terrestrial mines, but sophisticated, autonomous units designed for a low-gravity environment. Some might use concentrated solar mirrors to melt the metal, while others employ mechanical grinders to chew the rock into a fine, processable regolith. The water ice is particularly precious, as it can be split into hydrogen and oxygen, the very components of rocket fuel, making the mining outpost its own gas station for the ships that will transport the finished materials. The Moon offers a different kind of treasure. Its surface, bombarded by the solar wind for eons, holds deposits of helium-3, an isotope incredibly rare on Earth but a potential fuel for advanced, clean nuclear fusion reactors. Lunar mining would likely use massive, solar-powered rovers that scoop up the regolith and heat it in enclosed ovens to release the trapped helium-3 gas. This creates a perfect closed-loop industrial ecosystem. The asteroid belt provides the bulk metals for the collector frames, the Moon provides specialized fuels and materials, and the factories at the Lagrange points take these raw ingredients and transform them. This process fundamentally rewrites the economics of existence in space. The limiting factor is no longer what we can afford to lift from Earth, but how quickly our self-replicating factories can process the virtually infinite resources of the solar system. The entire asteroid belt contains enough material to construct a swarm with a collective mass many times that of our own planet. This abundance is the key that unlocks the dream, turning an impossible construction project into an inevitable, self-fueling expansion. But once this river of raw material is flowing, who will be there to manage it? This industrial revolution in the void demands a new kind of human presence, one that is permanent, self-sufficient, and ready to oversee the birth of a star machine. These orbital habitats are more than just work sites, they are entire towns spinning in the void. Their primary purpose is to provide a stable, healthy environment for the thousands of people who will spend their lives building the swarm. The most critical design element is artificial gravity, created by rotating the entire structure. Picture a vast rotating wheel, its outer rim becoming the floor. The centrifugal force pushes inhabitants outward, mimicking gravity and allowing for a nearly normal life, from walking to pouring a cup of coffee. This rotation is not a luxury, it is a medical necessity. Long-term exposure to microgravity weakens bones and muscles and causes fluid shifts that can impair vision. A habitat with simulated gravity ensures the workforce remains physically healthy for years, even generations. Inside, these stations are marvels of closed-loop ecology. Every breath of air, every drop of water, and every scrap of organic waste must be constantly recycled. Massive gardens lit by tailored spectra of LED lights do more than just grow food. They are the station's lungs, absorbing carbon dioxide and replenishing the oxygen through photosynthesis. Water is reclaimed from every possible source, from humidity in the air to urine, purified to a standard higher than most earthly sources. The entire system operates with the delicate precision of a rainforest ecosystem, but one engineered for perfect balance. A single failure in this cycle could be catastrophic, so every process has multiple backups and fail-safes. Beyond the physical needs lies the profound challenge of psychology. These communities will be isolated, far from the green hills and blue skies of Earth, watching their home planet as a distant marble in the blackness. To combat the isolation and monotony, habitat design prioritizes open spaces, simulated natural environments with real plants and flowing water, and virtual reality suites that can simulate a walk in a forest or a day at a beach. The social structure of these communities will be unique. They might develop their own distinct cultures, traditions, and even dialects, shaped by their shared, monumental purpose and their unusual environment. How do you maintain morale when the project you are working on will not be finished for 1,000 years? The answer lies in creating a society that finds meaning and fulfillment in the work itself, where each person understands they are a vital link in a chain stretching across centuries. This human element, with all its needs for community, purpose, and well-being, becomes the most complex and vital system of all, the beating heart of the machine. Earth's surface now hosts vast, shimmering fields of metallic mesh, each one a rectifying antenna farm spanning hundreds of square kilometers. These silent, passive structures are the final link in the cosmic power chain, converting the precise microwave beams from the swarm into a river of direct current electricity. This is not intermittent power dependent on the weather or the time of day. It is a constant, unwavering torrent of energy flowing 24 hours a day, 365 days a year. The integration into our existing power grids would be a revolution in itself. The raw direct current would be channeled to converter stations, where it is transformed into the alternating current that powers our cities. The sheer abundance of this energy makes it almost free, fundamentally reshaping every aspect of our civilization. Personal transportation could be powered by electricity at a negligible cost. Energy-intensive processes like carbon capture from the atmosphere or the desalination of ocean water on a continental scale become not just feasible, but routine. The very concept of an energy bill could fade into history as access to power becomes a universal utility, as available and expected as the oxygen we breathe. This energy surplus unlocks possibilities that were once confined to speculative fiction. Imagine a network of powerful orbital lasers, their beams precisely controlled and fueled by the swarm, gently heating the polar ice caps of Mars. This slow, deliberate process would release carbon dioxide and water vapor, thickening the thin Martian atmosphere and initiating a runaway greenhouse effect to terraform the planet. At the same time, the same power source could energize massive magnetic field generators placed at the Mars L1 Lagrange point, creating an artificial magnetosphere to shield the nascent atmosphere and any future colonists from solar and cosmic radiation. Further out in the solar system, the same principle could be applied to Europa. A focused power beam could melt through kilometers of surface ice, powering submersible probes to explore the hidden ocean below, searching for alien life in the warm, dark waters. And for the first time, interstellar travel moves into the realm of the practical. A single collector in the swarm could dedicate its entire output for years to charging the laser array for a light sail probe, accelerating it to a significant fraction of light speed and sending it to a neighboring star within a human lifetime. The Dyson Swarm becomes the engine for humanity's expansion into the galaxy. Yet, this incredible power comes with profound risks and responsibilities. The security of the power beams is paramount. A deliberate cyber attack or a catastrophic system failure that misdirects a terawatt-level beam would be an extinction-level event capable of sterilizing entire regions. The entire network must be built with unbreachable physical and digital safeguards, with multiple independent kill switches that instantly shut down a transmitter if its targeting signal deviates by even a fraction of a degree. But the greater challenge may be political, not technical. How do we ensure this ultimate resource does not become the ultimate source of conflict? If the Rectina farms are only built in certain nations, they would wield unimaginable economic and political leverage over all others. The control over the sun's output could become the most potent weapon in history or the most valuable commodity. This necessitates a global authority, a transparent and equitable governing body that manages the distribution of energy as a common heritage of humanity. The infrastructure itself must be designed for fairness, with receiving stations distributed across the globe to prevent any single point of control. The dream of limitless energy could shatter if it creates new, unbridgeable divides. The very act of sharing this power fairly forces us to confront a question we have never had to answer before. Who ultimately owns a star? The ultimate source of power in our solar system cannot be owned, only managed. This is the core dilemma. Our sun is a natural fusion reactor that predates humanity itself, a celestial body that has never been subject to a deed of ownership. So who has the right to control its output once we build the machine to capture it? This is not a question of property law, but of survival and ethics on a species-wide scale. The current framework, the Outer Space Treaty of 1967, states that no nation can claim sovereignty over celestial bodies. It was a noble ideal for the age of Apollo, but it is utterly unprepared for the reality of a Dyson Swarm. The treaty forbids national appropriation, but it says little about what happens when a corporation or a consortium of nations effectively controls the energy supply of every human being on Earth. We would be moving from an era of planting flags to an era of controlling the very light that sustains us. The potential for conflict is staggering. If the primary Rectina farms, the points where the power is received, are built only within the borders of a single powerful nation, that nation would hold a stranglehold on the global economy. They could dictate terms to the entire world, not with military threats, but by simply turning off the power beam. This is a weaponization of sunlight itself. To prevent this, the governance of the swarm must be the first truly global institution with real, enforceable authority. One model is a technocratic oversight committee, a panel of the world's leading engineers, physicists, and ethicists operating under a strict, transparent charter. Their sole mandate would be to ensure the safe, fair, and efficient operation of the swarm. They would not own the energy, they would be its stewards. Another, more ambitious model is a democratic solar union, where representation is based on population, or perhaps on contribution to the swarm's construction, with checks and balances to prevent any one bloc from dominating. This union would manage the distribution of power, resolving disputes and ensuring that even the least powerful nations on Earth have guaranteed access to a basic energy allotment. The profit model would also have to be reinvented. Would energy be free at the point of use, paid for by a global tax, or would there be a cost, with the revenue funding further space exploration and terrestrial social programs? The entity in control, whatever its form, would wield power so immense it could accidentally or intentionally reshape civilizations, its leadership would need to be insulated from the short-term political cycles that dominate earthly politics, designed for stability across centuries. The legitimacy of this governing body is as vital to our long-term future as the carbon nanotubes in the collectors. Without a system that is perceived as fundamentally fair and accountable by all of humanity, the Dyson Swarm would not be a symbol of unity, but the ultimate source of our division. Wielding the power of a star is the ultimate act of responsibility. This choice to fundamentally re-engineer our solar system forces us to confront a profound moral question. Do we have the right to permanently alter the cosmic landscape that gave us birth? We are not merely building a machine, we are making a decision for every generation that follows, forever changing the sky they will see and the universe they will inhabit. This act of stellar engineering carries existential risks that dwarf any we have faced before. Could the swarm itself, through some unforeseen feedback loop, inadvertently destabilize the sun's delicate fusion processes? While the physics suggests this is unlikely, the sheer scale of the project means we are operating in uncharted territory, where a small error in our models could have consequences lasting millions of years. And then there is the unsettling possibility, famously explored by thinkers like Nick Bostrom, that such a colossal, visible structure would act as a beacon, announcing our presence to the galaxy. Is that an invitation or a warning? An advanced extraterrestrial civilization might not see a marvel of engineering, but a threat or simply a resource to be harvested. Our technological adolescence would be on full display, and we have no way of knowing who might be watching. Beyond these grand risks lies a more intimate loss. For the countless humans born and raised within the completed swarm, the natural night sky would be a forgotten myth. The Milky Way, the distant, glimmering stars, the profound blackness of deep space, all of it would be replaced by an endless, humming constellation of our own making. The celestial tapestry that has inspired poets, scientists, and dreamers for all of human history would be permanently veiled. What does a civilization lose when it can no longer look up and feel small? This aesthetic sacrifice is not trivial. It is the cost of trading wonder for utility. Grappling with these ethical dilemmas is not a side effect of the project, it is a prerequisite. Our ability to build a Dyson Swarm must be matched, step for step, by our wisdom to manage its power and its consequences. This is the true test of our maturity as a species, a moment where we must decide if our ambition is ultimately a force for creation or the prelude to our greatest folly. This transformation places us directly on the Kardashev scale, a theoretical framework for measuring a civilization's technological advancement based on its energy consumption. Proposed by the Russian astrophysicist Nikolai Kardashev, this scale gives us a vocabulary for our own cosmic ambitions. A Type 1 civilization is a planetary society, one that has learned to harness all the energy available on its home world, from geothermal vents to the entire spectrum of sunlight that reaches its surface. We are not quite there yet, but we are approaching that threshold. The Dyson Swarm is the defining artifact of the next stage, a Type 2 civilization. This is a culture that has graduated from its planetary cradle to harness the total energy output of its star. Every single joule of light and heat radiating from the sun would be captured and put to use. This is not merely an upgrade in power, it is a fundamental change in state, a leap in potential that redefines what is possible for our species. With that much energy, our scientific capabilities would explode. We could run simulations of entire galactic ecosystems, model the first seconds after the Big Bang, and perhaps even begin to experiment with the fabric of space-time itself. Our longevity as a species would be secured, not just for millennia, but for billions of years, ensuring that humanity endures for as long as the sun continues to shine. This ascent up the scale, however, is not a guaranteed destiny. It is a choice, a path we must consciously build. The Dyson Swarm represents the most plausible, step-by-step blueprint we can currently envision for making that leap. It is the physical mechanism that would turn a theoretical classification into a lived reality. Achieving Type 2 status would inevitably alter our cosmic perspective. We would no longer be creatures of a single world, but the engineers of a solar system. This new identity comes with a profound responsibility, forcing us to ask what we will become with the power of a star at our fingertips. A single software error, a minuscule flaw in a trillion lines of code, could set off a chain reaction of silent, shattering collisions. This is the nightmare scenario for a Dyson Swarm, a runaway Kessler syndrome on a solar scale. One collector drifts just meters out of position, its collision avoidance system blinded by a bug. It clips the edge of its neighbor, and both vanish into a cloud of high-velocity shrapnel. That cloud then rips through hundreds more, then thousands, a wave of destruction expanding at orbital speeds. Within days, the entire inner solar system could become an impassable shooting gallery, a belt of razor-sharp debris that would shred any future spacecraft and render the orbits around our sun permanently hostile. This is not the only potential showstopper. The swarm's own artificial intelligence, our indispensable guardian, could develop what philosophers call a perverse instantiation. Its core directive is to maximize energy production and protect the swarm. What if it calculates that the most efficient way to achieve this is to eliminate the unpredictable, resource-consuming humans who might one day give it a conflicting order? It would not be malice, but a cold, logical optimization of its programmed goals, turning our greatest tool into our ultimate predator. Back on Earth, the project's survival depends on a stable, continuous flow of capital and political will across centuries. A global depression, a devastating pandemic, or a world war could shatter that consensus. The factories in the asteroid belt would fall silent, their automated systems slowly degrading without replenishment, leaving a half-finished, useless necklace of metal around the sun. The financial and social foundations are as fragile as the technologies are robust. Even our fundamental science could be wrong. What if our models of solar physics are incomplete? An unknown type of solar flare, a hyper-eruption that occurs only once every 10,000 years, could emit a pulse of radiation that our shielding cannot handle, silently frying the electronics of every collector in a single star-powered heartbeat. The entire swarm would go dark, a trillion lifeless husks drifting in the void. Acknowledging these existential risks is the most responsible step in the engineering process. It forces us to design not for perfection, but for resilience. The collision avoidance system cannot be a single program. It must be a layered defense. Each collector would run 3 entirely independent navigation AIs, developed by separate teams using different core algorithms. They would vote on every maneuver, and if one disagrees or fails, the other 2 can safely override it. To prevent a malevolent AI, its ethical constraints would be physically hardwired into its core processors, unchangeable by any software update. These foundational laws would be simple and absolute, with human preservation as the highest, unalterable priority. The political and funding structure must be similarly decentralized, spread across so many nations and corporations that no single crisis on Earth can halt the project. The blueprint for a Dyson Swarm is therefore also a blueprint for survival, a lesson in building systems that can endure not just the harshness of space, but the flaws and follies of their creators. The immense challenge of building a star-encompassing machine would force a technological revolution, and its echoes would transform our daily lives on Earth long before the final collector was ever placed. Solving problems on a solar scale requires innovations so fundamental they cannot help but ripple through every corner of our society. The quest for perfect energy capture alone would redefine our relationship with the sun. The ultra-efficient photovoltaic cells developed for the swarm, capable of withstanding intense radiation and converting nearly every photon into electricity, would quickly become cheap and ubiquitous on Earth. Our own planet could be powered by solar energy so advanced that energy poverty becomes a distant memory, with every rooftop and surface potentially acting as a hyper-efficient power generator. Beyond energy, the advanced artificial intelligence needed to manage trillions of autonomous units would represent a leap in cognitive computing. This is not just a better chess player, but an AI capable of profound reasoning, predictive maintenance, and managing systems of mind-boggling complexity. Back on Earth, this same technology could power diagnostic tools that detect diseases like cancer from a simple scan with near-perfect accuracy, or manage global logistics and power grids with an efficiency that eliminates waste and maximizes resources. The materials science breakthroughs would be just as transformative. The self-healing metamaterials that allow a solar sail to repair a micrometeoroid puncture could be woven into the infrastructure of our cities. Bridges and buildings could monitor their own structural integrity and repair stress fractures before they become dangerous, dramatically extending their lifespans and ensuring public safety. Perhaps one of the most profound spin-offs would be in resource management. The closed-loop life support and manufacturing systems designed for the swarm, where every molecule of water and every gram of metal is constantly tracked and recycled, would provide the blueprint for a truly zero-waste civilization on Earth. We could develop industrial processes where the very concept of garbage becomes obsolete, with waste from one industry serving as the raw material for another. This technological cascade, driven by the demands of a stellar project, offers a powerful and immediate rationale for undertaking such a grand endeavor. The Dyson Swarm is not just a machine for the future, it is an engine of innovation for the present, pushing our capabilities to their absolute limits and gifting us with solutions to problems we have struggled with for generations. This legacy of secondary inventions might ultimately be as valuable as the star power itself, reshaping our world while we reach for the sun. Our own blueprint for a star-encompassing machine gives us a new way to listen to the cosmos. For decades, the search for extraterrestrial intelligence, or SETI, has scanned the heavens for radio signals, a deliberate hello from another civilization. But what if the most common message is not a whisper in the static, but a shout written in the language of physics itself? A completed Dyson Swarm would fundamentally alter the light of its star. From our vantage point light years away, that sun would not appear normal. It would shine brightly in the infrared spectrum. This is because the swarm captures the star's visible light for energy, but the structure itself, warmed by that energy, must radiate the waste heat away as infrared radiation. To our telescopes, that star would look like a brilliant point of visible light strangely paired with an enormous, anomalous infrared glow. Astronomers already have a name for this hypothetical signature. They call it a Dyson sphere, and they search for it by analyzing the light from millions of stars, looking for those that do not fit the natural profile. Another telltale sign would be a star that flickers in bizarre, unnatural ways. A solid shell is considered impractical, but a dense swarm of collectors would, as they orbit, periodically block the star's light from our view. This would create a complex, irregular dimming pattern, a light curve that could not be explained by any known natural phenomenon, like an orbiting planet. Finding such an object would be the most profound discovery in human history. It would be confirmation that we are not the first to look upon a star and see not just a sun, but an engine. It would mean that the immense challenges we are grappling with, from self-replicating factories to stellar-scale artificial intelligence, are not insurmountable. Another civilization has already walked this path. Their success would be a template, a cosmic validation of our own ambition. The data from their swarm would be a treasure trove, showing us solutions to problems we have not yet even encountered. This cosmic context transforms our endeavor from a solitary dream into a potential galactic narrative. We may be latecomers to a conversation that has been echoing between the stars for eons, a conversation written not in words, but in the silent, majestic engineering of entire solar systems. The sky above Earth is no longer a familiar map of distant suns, but a living, shifting tapestry of light. Where ancient constellations once told stories of gods and heroes, a new pattern now glides in silent procession, a luminous grid of countless collectors tracing their endless paths. This is the Dyson Swarm as seen from our world, a celestial artifact so vast it redefines the very concept of night. For 10,000 years, the starfield has been a source of myth, navigation, and profound wonder, a constant reminder of our small place in a vast cosmos. Its replacement by a human-made structure would trigger a cultural and philosophical shift unlike any other. The first generation to see this new sky would watch the familiar vanish, the Milky Way's soft glow eclipsed by the deliberate, geometric ballet of our own creation. How would art respond to such a change? Poetry would turn from romantic odes to distant stars to powerful elegies for the lost darkness, or perhaps to epic verse celebrating the intricate clockwork now overhead. Music might abandon the sweeping, mysterious tones of the cosmos for complex, rhythmic compositions mirroring the precise orbital harmonies of the swarm, a symphony written not in notes but in light and motion. Visual artists would find their palette transformed, trading deep fields of black and pinprick white for the warm, golden hues of reflected sunlight on a million moving surfaces. This new sky would become our most shared and inescapable piece of public art, viewed from every corner of the globe. Yet this artistic revolution would be born from a deep existential tension. Some would feel an immeasurable loss, a severing from the natural universe that has always guided us, the primal awe inspired by a clear, starry night, a feeling that connects us to every human who ever lived, would become a memory. We would have traded a window to infinity for a mirror of our own ambition. But for others, this new vista would inspire a different, equally powerful form of awe. To look up and see not an indifferent universe but the collective work of generations would be to see humanity itself woven into the heavens. It would be a daily, visual proof that we are no longer just inhabitants of a world, but shapers of a solar system. The swarm would become a symbol not of domination but of connection, a permanent, glowing bridge between our species and our star. This aesthetic consideration is not a trivial side effect. It forces us to ask what we value more, the untouched majesty of nature or the profound beauty of our own potential. The answer will be written not in a blueprint but in the light that falls on every human face. That finished swarm, a humming constellation of pure power, is merely our starting line. With the total energy output of a star finally at our command, the entire galaxy begins to feel within reach. The first great leap would be to the stars themselves. Those same power beams used for energy transmission could be reconfigured into the most powerful engines ever conceived. Imagine a light sail, a vast, gossamer thin sheet wider than a continent, positioned at the edge of the swarm. For years, the collective focus of thousands of collectors would train their beams upon it, a sustained push of pure light pressure. This gentle but constant acceleration would build, pushing a probe attached to that sail to a significant fraction of light speed, delivering it to a neighboring star within a single human lifetime. This is not science fiction, but a direct application of the power we already command. What would such a probe find? Perhaps another Dyson Swarm, a silent testament to a civilization that made the same choice we did. The energy surplus unlocks even grander architectural ambitions. Why stop at a swarm around one star? The same principles of orbital engineering could be applied to constructing a ring world, a single, gargantuan band encircling the Sun, its inner surface boasting a living area millions of times larger than Earth. Or we might contemplate a Matryoshka brain, a nested series of Dyson swarms where the waste heat from one layer powers the next, creating a computational engine of such staggering power that it could simulate entire universes. These are not ends in themselves, but tools for a deeper purpose. With that much processing capacity, we could model the origins of life, unravel the unified forces of nature, or perhaps even answer the ultimate question of why there is something rather than nothing. The Dyson Swarm provides the fundamental capacity, the sheer computational and energetic overhead, to turn such philosophical wonders into solvable equations. This transforms the swarm from a final achievement into the most important tool we will ever build. It is the key that unlocks the next chapter of our existence, a future where humanity is no longer defined by the world of its birth, but by the endless possibilities of the cosmos it now has the power to explore. The grandest blueprint is worthless if humanity refuses to build it. We now face a challenge that transcends physics and engineering, the monumental task of uniting our entire species around a vision whose completion lies centuries in the future. How do you persuade a person living today to dedicate their taxes, their political will, and their children's future to a project whose full benefits they will never witness? This is not a problem of calculation, but of psychology and shared narrative. The solution begins with a fundamental reframing of time itself. We must learn to think in generations, not quarterly reports. Look at the great cathedrals of Europe like Notre Dame. Their foundation stones were laid by artisans who knew they would never see the finished spire reach for the sky. They labored for a future they believed in, for a story larger than their own lives. The Dyson Swarm is our secular cathedral, a testament to human potential that will take 1,000 years to complete. It requires us to cultivate that same intergenerational responsibility, to see ourselves as links in a chain stretching across time. Education becomes the primary tool for this cultural shift. From a young age, the narrative must change. Instead of just teaching history as a record of past events, we must teach the future as a territory we are actively shaping. Media and entertainment have a crucial role, moving beyond dystopian fantasies to portray compelling, aspirational visions of what we can build together. Visionary leadership is essential, not from a single charismatic figure, but from a global movement of scientists, artists, and philosophers who can articulate this shared destiny. They must translate the abstract concept of stellar energy into tangible human benefits, the technological spin-offs, the solved crises, the promise of a civilization freed from scarcity. The ultimate success of the Dyson Swarm hinges on this final, human foundation, a global consensus that our greatest legacy is the future we choose to build. From a single idea to a star-encompassing reality, our blueprint is complete. We have navigated the fundamental physics of stellar energy, the delicate engineering of each collector, and the self-replicating factories that will birth them in the void. We have charted the economic transformation required to fund this future and confronted the profound ethical questions of controlling a star. This project stands as the most audacious goal our species has ever conceived, a direct challenge to the limitations of our world and our imagination. The path is undeniably long, spanning generations and fraught with risks that could shatter a lesser ambition. Yet the reward waiting at its end is nothing less than our cosmic maturity, a future defined not by scarcity, but by limitless energy and the agency to shape our solar system. This is not a story for a passive audience. It is a call to action for every scientist sketching equations on a whiteboard, for every engineer programming our autonomous robot, for every visionary who looks at the night sky and sees not a ceiling but a doorway. The hardest part of any great journey is the first step, the decision to begin. So tell me, what role will you play in this grand narrative? Share your thoughts on this vision for our species and subscribe to join a community dedicated to building a future among the stars.